summer school in Italy, in Bologna last summer. But last summer we got similar number of students, about 30 students. But there were only one mathematics student. All the students come from computer science, bioinformatics, usually all working with using computer vision things. So therefore I must modify the contents. It seems that most of you are from the mathematical science, or how many of you are from a mathematical background? So this time it seems we have a lot of more mathematicians. So therefore I'm planning to modify the lecture again, because last year in the end we need to drop most of the mathematics, and then we just go through the algorithm. Even the student need to solve exercises nearly every week. So I was there, I think the teaching was 1 week, I stayed there 1 month, I stayed there for 2 months. The students every week they have exercises they need to implement, and that was very, very good. But it seems now you see that maybe we should try to do more mathematics. So also I have been thinking a little bit about, because how many of you have been working with the image processing? Yeah, so therefore, so I'm planning, you see there are essentially two parts. The first part just some elementary partial differential equation thing for image processing. So the second part was more related to, you see, like a segmentation thing. You can use it for image segmentation, surface processing, a lot of pattern recognition, or you see data mining. So that one especially I want to introduce a few of the very advanced, you see, in the past half a year or so, there came out quite a number of very good and fast and very stable algorithms. But now it looks like even the first part may be too easy for most of you. So yeah. So the first part I was essentially just so how many of you have been working with like the ROF model, the routing Osher-Fatami? She must know, right?
If we do ROF model.
Right. So in that case, maybe we can still. So the first part, I have some slides, but still, maybe mostly we still use a Blackboard and try to go through very quickly. So today maybe the most elementary PDE, and tomorrow some fast algorithm for the elementary ones. And from next Monday we can switch to the new stuff. And those new stuff is really very good. It's very new. It's mostly of them are developed in the last half of 1 year. It has been tested very, very fast, very, very stable. So yeah, so in that case, maybe we still go through the first part, which is very elementary. Maybe from some of you it's nothing new. If it's nothing new for you, just a little bit patient. So we start with new things maybe next Monday. Yeah. Right. So yeah. So the first part, I have some slides. Maybe still you see that I can mostly use the. Yeah, those might be too easy, so let's skip most of the easy things. Yeah, so therefore you see that using PDE for image processing, at least for math students, mostly you see that, yeah, my group, just as Professor Lee introduced, so my original background was in scientific computing. I was a dominant composition, parallel computing, inverse problems. So that's also many years ago. I know Professor Lee. So we started to work on image processing from around 2000, so about 12 years. So we have been working on quite a number of very fast algorithms, and recently So we are working quite a lot with, you see, interface problems, surface processing, and image segmentation. So that's my background. So therefore, PDE is something we know very well. That's something we've been working. So the most, you see, the first thing you see that you use the image partial differential equation for image processing is essentially you start with the heat conductivity equation, right? So this is the time t, this is Laplacian. So therefore you see that assume you have a noise image UD. So therefore just take a simple case. You see this is 1D01. So here is a noise image and the solid one is a real image. So therefore you see that if you want to remove noise, so essentially what you do that you just put this one as the initial temperature. Put the noise as the initial temperature. And then you see the high temperature go down, the low temperature will go up. So essentially you see that after a little while, so therefore you see that the oscillation will disappear. So here the oscillation will disappear. So that's the most easy way to use a partial differential equation for image processing. So this is also mostly you see that my students start with me working on image processing. This is the first thing they test. You see, give them a noisy image. So 1D is the signal. You put in the initial value, solve the equation, and then you can see the noise disappear. But the problem that you cannot continue for very, very long time, right? If you just, you see, matching the T for a little while, the low temperature goes up, high goes down, and then you smooth the noise. But if you continue, you see those two, so here is much higher, here is lower, and you see the two constant will become just one constant, and then you have a smooth too much. So this is the most easy thing for image processing. It seems a lot of things for image processing can be, you see, somehow regarded to start from here. You see that mathematically there is another explanation. So especially if the domain is infinite. So mostly for image processing we can consider a simple interval, right? If the domain omega is infinite, so this equation has a fundamental solution. How many of you have been learning the fundamental solution for the heat conductivity equation? Yeah. So this is most probably this is the first thing you learn for a PDE course, right? So this equation has a fundamental solution, and this is the so-called fundamental solution for this equation. So therefore you see here, if it's 1D, just x square. If 2D, you see that it's a vector square. This is the fundamental solution. So therefore, essentially using this one as sometimes we use a UD, sometimes you use 0. So this one is the initial temperature. So solve this equation. That was the same. You see, you convolute the noise image by this kernel. This is an explicit formula for the solution. If the domain is infinite, is a whole space, right? So therefore, you see that if you look at this formula, so therefore people working with image processing, especially you see engineering image processing, you already know something. So this is essentially, you see that mostly you see image processing. So here you put the sigma. This T is called sigma. Here you see also you take sigma. So this is essentially the Gaussian kernel. So that means that you see that you solve that equation using this as an initial temperature. So essentially it was a convolute your noise image with a Gaussian kernel. So therefore the fundamental solution has a very simple form, right? The fundamental solution is essentially if you draw it. So here this is the fundamental solution. I think it was essentially minus 3 sigma and positive 3 sigma. Here is non-zero, but it's nearly 0. That's a fundamental solution. So that was essentially, you see that you convolute your image with such of a kernel. So it's an averaging process. You average your image. So essentially you solve this equation was essentially use this function to average this image. But when you do the averaging, so therefore you see the maximum weighting is here. We are getting a little bit away, the weighting is smaller. So therefore the integral of this one is always equal to 1, so it's an averaging process, and this converges to a delta function. So therefore you see that you can see that essentially, I think that's also the next slide. What I'm seeing was maybe someone was taken away. Yeah, taken away. So therefore you see that this process, so in the electronic engineering, so this is essentially is one version of the Wiener filter. One version of the Wiener filter was exactly just using Gaussian kernel and do smoothing. So therefore you see that, especially you see that because the PD image processing is relatively new compared with you see digital image processing, especially you see the engineering community. And quite often you see that the methods used there, you can find some corresponding mathematicals to explain it. So this is mostly, I'm always using this example as a starting point for using partial differential equations for image processing. Especially this function you should encounter quite a lot for image signal processing. This mostly you see that mostly there is a sigma here. So t, so in terms for this partial differential equation, t is the time. So therefore you see that so this sigma is related to t. So if you solve this equation for longer time, so that was equivalent to use a much wider, you see that, and then this one become wider, so which means that you average over a large number of pixels around that point. If t is very small, you just average a few pixels. So therefore you see that here, how far away, how long time you will solve this PDE. So essentially it's another way to control, you see that how many pixels you want to average. How many pixels to average. So this is one of the starting point. So therefore you see that one weak point is a discontinuous function cannot be a solution for this problem, because the solution must be continuous. This is also, you see that reflected, you see by this example, partial differential has a smoothing property. Whenever t is bigger than 0, this jump will disappear, it will be smoothed. So you have a sharp layer instead of you have a very sharp jump, and this is the weak point. You see that this layer is even getting bigger and bigger, so it's getting more and more blurred, and this is the so-called blurring effect of this filter. But however, yeah, so therefore you see that was you see that linear equation is more related to like the paranormalica for the nonlinear case. Here you see there is another case to understand the image processing, that so assuming sometimes you use UD, sometimes you use 0. So assuming this is noise image, assume you know the noise level, and this is in statistics, this is called the standard deviation. If you know the noise level, so here is the L2 norm. So here is essentially U minus UD square dx equal, assuming you see that you know the noise level, right? So therefore you see you want to remove the noise. So therefore you see that a noise, so there's you see that I don't know if there exists a standard definition for noise. So a noise is something which is very oscillatory, right? So therefore you see that you have and then it's a very oscillatory. So therefore something is very oscillatory, so that means the gradient is very high if something is oscillatory. So oscillation functions, the gradient will be very, very high, right? So here is mostly this is the gradient. So therefore, if a noise image, the gradient will be very, very high. And for normal signal, you see that the gradient will be lower than the noise image. So therefore, you see that the true signal is also satisfy this one. So So they are infinite many signal. If you give a noisy image, they are infinite many image which satisfy this noise level. You want to remove the noise, so therefore, and then you see one way that you just minimize the derivatives. So the derivative. So here this is a definition of the of the seminorm of U. So therefore, you want to remove the noise. So how do you remove the noise? It's essentially, you see that you try to find a function which has the smallest oscillation, So therefore, you try to find. So here there are infinite many image satisfy this one. You try to find one which has the smallest oscillation. So this will be, if you do this one, so you will remove the noise, right? So therefore, essentially, you see this looks like a constrained minimization, and then you can put this one as a Lagrangian. So therefore, you minimize U, maximize with lambda. Minimize the U, so here you have a gradient. So this is essentially defined by this one. So therefore, here you have a gradient operator. Here is just L2 square. So therefore, you see that if you minimize the U, so that will be equivalent to solve this partial differential equation. Do you know how, if you minimize the U, you will get this partial differential equation? Do you know how to derive it or not?
I guess
Most of them no. Yeah, so I think this is also one of the, maybe not the first thing you learn in the partial differential course, the second one, the variational part. I think the first part you learn the classical solution, but the second part you learn the variational solution. So therefore, yeah, that's a Euler Lagrangian. So here do variation and do integration by part, and you will get this equation. Also, you see that here is coming from the interior point. On the boundary, you also get some term. What kind of boundary condition you should get for this equation? Sorry? That's right. So on the boundary, so mostly you see if you use integration by or the Green's formula, so you will get such a term du dn times arbitrary v, and this should equal to 0, and then you need to impose this Neumann boundary condition. And so therefore, essentially minimize u is equivalent to solve this equation with the Neumann boundary condition. Minimize, maximize with lambda, you get back this constraint. So therefore, solve those two equations, you can determine both u and lambda. Under some conditions on the noise, under some condition you can always guarantee lambda is bigger than 0. Right. So therefore, this is, you see, again, you solve, you get a partial differential equation. But you see that here you get a partial differential equation through like a minimization concept. The previous one is actually like you get the time evolution. So therefore, you see that these methods, if you, especially you see this norm, if I have a discontinuous function, can this norm, is this norm finite or not well defined? If you have a function which is discontinuous, if a function is discontinuous, this norm does not exist, no matter in 1D, 2D, arbitrary D. So discontinuous function, this norm is infinity. So therefore, essentially, you see that you minimize this norm, and the solution will be still cannot have discontinuities. You can have sharp layers, but you will not be able to have a discontinuity. So therefore, you see, similar to the previous equation. So this will remove the noise. Mostly you will get sharp layers, but however, you cannot have a discontinuous. If your true image had a discontinuity, so this part, the Laplacian part will blur the discontinuities. Yeah, discontinuity. So there is another thing, you see that, so here you see we assume the noise level is known. So very often you see that you don't know the noise level exactly. So therefore you see that we can just simply forget about this one. This lambda should be related to the noisy level. So therefore you see that assuming we don't know the noisy level, so just ignore this one, just consider this equation but with a fixed lambda. And so therefore you see that if lambda is big, what kind of effect you will get? Just look at this equation. If lambda is big, if lambda is big, so you divide the lambda, you get lambda inverse, you can see that this term is nearly negligible. So therefore when lambda is very big, your solution U will be very close to the noisy image. So that means that you don't remove too much noise, or numerically you can observe, you see you retain nearly all the noise if you use very big lambda. On the other hand, you see that if lambda is very small, the lambda should be always positive. If lambda is very, very small, what kind of effect you should get? That's right. So if lambda is 0, you just get Laplace equal to 0, you get a harmonic function. So therefore one of the solutions of a harmonic function is just constant. So you get something very, very smooth. That means that you remove too much signal. So therefore in practice, if you don't know the noisy level, so essentially you see that a bigger lambda, you remove very little noise. A smaller lambda, you remove too much noise, you smooth too much. So therefore a good balance is that you choose a lambda which is proper to your noisy level. There are a lot of papers working on how to select this lambda parameter. You see how do you automatically select it. So therefore you see that. But however, I'm not sure you see that some of those methods are really, you see, industrial accepted. There are a lot of different variants. But how many of them are really used in practice, I'm not sure. But at least from here you can see that the lambda controls how much smoothing you are going to do and how much noise you are going to remove. The next thing I want to say that you see that for images, so now image has a meaning because I have a discontinuity. If you plot a smooth function, there's nothing to see. So essentially somewhere is darker, somewhere is you can plot the surface where very beautiful, but if you plot it an image and then you see nothing. So therefore image has a meaning because it has a discontinuity. So therefore you see many of the, you draw something, you just sketch the edges and you know what kind of image it is. So therefore for a given image, the discontinuity is the most important. You see that. So here is this is the image, here is the plot. So you see that the discontinuity are the most important meaning for part of the image. So therefore processor image is a different processor surface. You get surface processing, you don't have discontinuity. But for image processing, you see how do you handle the discontinuity is the most crucial part. So you shouldn't alter the location and you shouldn't blur it. And also the best one, you shouldn't, you see that, modify the contrast. So therefore those are the crucial things for image processing, even may not be for surface processing. So that's the reason you see that the PV comes in. So therefore you see that the so-called BV functions, you see BV means bounded variation. So here you see that you plot such a 1D function, right? And so therefore the variation means how much the function value has varied. So you see first you vary from here to here, and then you come down there to here, and then come down, come up. So therefore is that the total variation of this function is essentially you see that this jump plus this jump plus this jump. So you see you sum together all those jumps. That's how much the function value has varied. First you vary from 0 to this value, and then you vary from here to here. So this amount is the variation, another amount of variation. So this, if you see sum all those variation, that's the total variation of this function. You see that for that function is in fact exactly equal to 0 to 1 f derivative, but you take the absolute value. So therefore for 1D function, if you just take the derivative, take the absolute value for that function, this is exactly equal to total variation. Because when the function increases, you just take the positive gradient. When the function decreases, you take a negative. So therefore, you see here is a negative, positive, and negative. So therefore, you see this is equal to the total variation of a function in 1D. And that's for a smooth function. You see, this function is non-smooth. And still, you see, you know what's the variation. You see, from here, you jump to there. And this jump, those are the variation. If you sum all the variation together, so that will be the total variation. So you see a function smooth is, if not smooth, so this will not be meaningful anymore, but you can still, you see, define the total variation. So in that case, you see, for this function, the total variation that you give an arbitrary mesh. So therefore, for 0, 1, so for 0, 1, so here is your region omega, and you have an arbitrary partition. So they are infinite many partition, right? Each partition from here, there is a jump. So here is from here there is a variation. But if you take a supreme of all the partitions which is satisfied such a one, and the supreme of this one in the limit will converge to the total variation of this function. So this is another way to define the total variation for functions which are not continuously differentiable. Even this one, you see that this definition is also very clear for 1D function, right? So you give a partition. So you partition into many intervals. You calculate the variation for each interval. You see that when this interval, mostly when this interval goes to 0, that variation converges to this total variation. So that one is also, you see, very intuitive. But however, even this definition is not easy to be extended to high dimensions. So there's another way, you see, that instead of doing this one, you see that using integration by part, 0, 1 fx v derivative. And this v derivative should be, you see, for all v functions which are infinitely continuous, compact, but the value is less than 1. So therefore, this is another alternative way to define the total variation for 1D function. For 1D function, total variation is very clear. There's a lot of you see, good definitions. So total variation means how much the function varied. And so therefore, you see that. And from here, you can see that a function has a bounded total variation. You can still have discontinuities, just if the variation is not too much. So if a function is, you see, if a function very oscillatory, and the total variation will be very high. So therefore, minimize the total variation, you will be still able to preserve discontinuity but kill the oscillation. But this is the total variation for 1D. I think introducing total variation to image processing, that's one of the major contributions for Stanley Osher. And that's the reason he gets so well known. I think also introduced this one was due to him. So for 2D functions, there is no easy way to see what's the total variation of a two-dimensional function. So therefore, we just use one of the definition, which is for 1D problem. So essentially, that if this is a 2D domain, fx, you take a divergence of a vector, and this vector is equal to p1, p2, and you ask the vector norm is less than 1. Also, C0 infinite. This is you see, this is one way to extend the total variation to the two-dimensional function. So this is one of the ways to extend. So another easy way to extend is that you can use another easy way to extend the total variation is that the TV. So this is one of the ways. Another easy way is that you see that you can. So this is total variation of all the one-dimensional functions. And this is the total variation along each vertical line. So therefore, you see that this could be also one way to define the. This is an easy way to extend the total variation from 1D to 2D. However, you see that this definition has been used for image processing, but has some disadvantages. One of the disadvantages is that this is not rotational invariant. So therefore, if you give a function, if you rotate it by a number of degrees, and then the total variation defined in this way will be different. So you get a different, you see that, and then the total variation will be different. But if you use this way of to define the total variation, and then it will be still the same if you rotate the image by any number of degree. And so this is one of the reasons you see that this is used quite a lot. Even this way is easy. You can easily think about. So therefore this is one way to extend the total variation to two-dimensional things. Yes?
So this the definition of the previous slide?
Yeah.
The bounded variation or?
Sorry?
This is called the bounded variation? No?
Yeah, this is the total variation. TV means the total variation of the function.
You know the bounded variation?
Bounded variation, mostly BV, you see bounded variation space. And this is the total variation for a given function. This is called total variation. If the total variation is finite, and then you code it, that's a bounded variation function of bounded variation. TV means the total variation of this function. If the total variation is finite, and this function has a bounded variation. Mostly the functional space is, we say BV space, but the total, yeah. This is just another variant of the total variation. So for 2D, you see that you can have different ways to define total variation. For 1D, I think there's only one way to define total variation. But for high dimensions, you can define total variation in different ways. So that's one of the ways, and this is the easy way. But however, it has some weak points. Right. So total variation, so this is a way to extend the total variation to high dimensions, and especially if you use this definition, you see that if you have a bigger domain omega, if a D is a subdomain, and you take the characteristic function of this subdomain, and then the total variation of this function will exactly equal to the length, of the boundary. Have you learned how do you prove this one, or? I think.
Yeah, some of the students know that.
I think maybe just for 5 lectures, I think it will not be possible for us to go through all the detail. Maybe, for example, like this one or this one, we can just skip it. Maybe later you can use it.
Calculation as exercise. Why don't you give homework?
Yeah, but this will not be easy. This homework will not be easy. I think you see one possibility you can later, maybe the student can use the seminars to go through those things. Because 5 lectures, I think we cannot go through all the details, right? So essentially, you see, if you have a domain, if a function which is equal to 1 inside, equal to 0 outside, and then the total variation of this function will equal to the length of that curve, and especially you see if a function is really differentiable, which means it doesn't have discontinuity, and you can prove that the total variation is essentially equal to this one. So therefore, if a function is differentiable, and then the total variation of a function is equal to ux squared plus uy squared dx dy. That's what you write here. If a function is differentiable. Yeah. And especially you see that this one means that if a function have a discontinuity, and that the total variation can still bound it. Yeah. So this is one of the advantage of the TV function. You see that you see like here you see this is mostly you see people when people write papers they write in this way. Precisely, you see this is only correct if the function is differentiable. If the function is not differentiable, this is not correct anymore. But people you see that mostly don't care. That's also you see that I was giving the lecture and one of the students came to me. He said, you see, why the papers when they prove something they always use a discretized. Because in the continuous setting, this is not correct. But in the discretized, mostly use a discretized. If you read all the paper for TV, when they prove something, mostly they use a discretized. You give a grid, and this is replaced by finite difference. In discretized, this is always correct. Because in the continuous setting, writing this way is simply wrong. It's not correct. It's just formally correct. Yeah. So therefore, this means that you see that if you use a TV, so therefore it will allow discontinuity. So therefore, you see, for vector function, you see that you can extend. You see, if a color image, you may have a 3, and here is only 2 vector. You can also, you see, extend the TV to vector ones. Maybe this is too much. We don't talk about this one. Yeah. So therefore, you see that this is essentially the routing Aushel-Fatami thing. So essentially, you see that similarly, originally here we put the square. So the square will not allow these continuous functions. But if we take a square away, this will allow, if you minimize the total variation, this will allow discontinuities. So therefore, you just replace the 2 by 1, here is essentially the total variation, and you still consider these constraints. So this will allow discontinuous solutions. It is, if you minimize this one, still use Lagrangian, so this will, you will solve this equation. And this is a well-known routing Aushel-Fatami model. This is a well-known routing Aushel-Fatami model. So I think it was from here, you see partial differential equation was stepping into image processing, and nowadays it's used quite a lot. And this is very elementary. And so therefore, you see how do you get is you use same Lagrangian, and you do the calculus variation, you come to here. Mostly, you see how do you solve it? So you add the ut variable, marching in the negative gradient direction. So therefore, you see ut equal to minus, and you get a positive again. So therefore, you use the time marching, or you don't have a 0 here. This is a typo. You solve this time marching equation. When t goes to infinity, and the solution of this problem converges to this one, and this is the solution of that one. So therefore, the routing Aushel-Fatami is that you still use the derivative to kill the oscillations. Yeah. But however, if you take a 2 away, put it 1 here, you kill an oscillation, but you will not kill the discontinuity. You will not kill the discontinuity. So this is the routing Aushel-Fatami. So essentially, you solve this equation. I think most probably, I can give this one as a homework to you, right? You minimize that function, right? So you minimize this function, you minimize total variation, and such that u minus u0 equal to sigma. You still define Lagrangian equal to u plus lambda. So here u minus u0 square minus sigma square. And then you see that the minimization of u essentially is equivalent to solve this equation. Do you think you can use the calculus variations to derive that you minimize this one will be equivalent to solve this one? Here you see that it's not precise mathematically. First, you see that this term is only correct when u has a derivative. Second, you see that this equation doesn't have a meaning when this is equal to 0. So it's still, you see, very formally. But however, formally, if you minimize this one, if you can derive this equation, that would be good. So how many of you may be able to derive this one, or you can have a try to see if you minimize u here, it will come to here.
Yeah, but in this case, if you solve this problem, it contains no information of sigma.
It contains
no information on sigma.
Oh, yeah, the noisy level.
Noisy level,
yeah.
If you solve this problem, you have just you determine the solutions.
Yeah.
It doesn't have any information related to that sigma. If you change the sigma, in that minimization problem, if you change the sigma, then the solution should be changed.
Yeah, this lambda should be changed.
Oh, okay.
Right. Because this lambda is really the noise level. Most of the small noise level give a big lambda, larger noise give a small lambda. So therefore you see that, so essentially you can use the noise level to determine lambda, or you can just, as we said in the previous case, you can just ignore this one, just using this lambda to, you just modify to see the different effect. So this is, I think this is for the ROF model. And so therefore you see that as for the linear case we have two approaches. So one approach is you directly use this equation. Another approach is you use this minimization. Also for the nonlinear case, so the first you get a nonlinear partial differential equation. So this is a nonlinear partial differential equation. For the nonlinear case, so therefore another version that essentially you see that if you use such a kind of a nonlinear partial differential equation, you still use this one as a noise image. So therefore if a G, so here this G depends on the solution U. If a G equal to 1 and this equation reduces to what? If a G equal to 1 everywhere. This is normally called the diffusion coefficient. If a G equal to 1, what kind of equation you get? You get reduced to the previous linear one. So therefore the paranormalic is that essentially you don't use a constant diffusion. I use a nonlinear diffusion. For example, the nonlinear diffusion can take several choices. One choice is this one, another choice is this one. And so therefore you see that this is nonlinear diffusion, and then you get another kind of a nonlinear partial differential equation. If you do this one, so therefore you see at the discontinuity and the gradient in a continuous sense, we can see that gradient equal to infinity there. At least the approach, if you have a grid, the gradient will approach infinity when the grid goes to 0. So therefore this goes to infinity. And so therefore the diffusion is 0 there. Both of those choices. So this is one choice for the paranormalic, this is another choice for paranormalic. So for both choices, the diffusion coefficient equal to 0 when there's a discontinuity. And so therefore you see in a not very precise mathematical way, you see that so if you have such a function, you see that you have a function here suddenly have a jump, you see that have a noise, and then you see that here the G gradient U, so here will equal to 0. So therefore in terms of a conductivity, so which means that this point has an insulation. So there's no conductivity. Conductivity equal to 0. So therefore the temperature cannot go from this side to the other side. So you exactly have an insulation. So therefore you see the conductivity can only do, you see that if you have several insulations, so if here's another point equal to 0, here another, if you have another jump, so which means the temperature can only conduct within the intervals. So which means that you can only smooth piece by piece. You will not smooth over here, so that's the reason you will not blur the jumps. So this is you use the partial differential to explain those things. So the noisy smoothing is essentially average with my neighbors, and then you see high noisy goes down, low noisy goes up. But that when you do that one over a jump, so here is a smooth here, the jump will smear out. But these kind of nonlinear diffusions, so you never smooth over a jump. So that's the reason you can keep all the jumps. I think this is where you see the two well-known nonlinear filters. So one is routing Aucher-Fatami, and this is the paranormalic. I think both still have a lot of influence in image processing nowadays. You see, in terms of partial differential and conductivity, this is a very easy explanation. So therefore you see that right? We have been talking about this one, right? We have been talking about this one. So this is the TV. And so therefore you see, especially paranormalic, so you see that if this is equal to 1, so this is essentially the TV. And paranormalic, this was somewhere here, so you see that you have different kind of extensions that combine the paranormalic with the routing Aucher-Fatami. Here is a lot of tests. So therefore you see that the routing Auger-Fatami methods, you see, it's very good in the sense that if you use it to smooth the image, it never miss any discontinuity. The discontinuity exactly preserved, even you don't move it by 1 pixel. So I think there's no other methods which can preserve the discontinuity so accurate and so good as the ROF. So I think that's a good point. If you really have a discontinuity here, if you use a routing Auger-Fatami, you never miss this one. You never miss the location. And that's essential for image processing. And also from the image here you can see, but you see that here you see that you never miss the discontinuity, But one of the problems you see that I think is that the routing Auger-Fatami has a staircasing. So which means that in the smooth region you produce a lot of small piecewise constant. And that's also you see that that's another problem. So which means you produce too many discontinuities. The true discontinuity are preserved, but you produce a lot of small discontinuity in the small regions. And so that's something you don't want. So therefore, sorry? Oil painting is also related to staircasing. Right? Oil painting you see like you have a layer by layer. Instead of you have a smooth region, you have a small layer region, like oil painting. I think oil painting and staircasing are same or similar. Yeah. So therefore you see that you preserve the edges very, very well, but you produce a lot of small staircasing, small steps, and that's well known. And so therefore you see that to overcome that one you can do something is like a P. So therefore you see if you know where have a discontinuity, you take a P equal to 1 there. If you don't have a discontinuity, you take a P equal to 2. But in practice, how do you do it? That's not easy, and also that's not a convex problem anymore. So therefore you see that there's another way to overcome the staircasing that you see here you minimize in order to kill the oscillation you minimize the total variation, right? But if I minimize the total variation of the second order, you see if a function oscillatory, the second order derivative will be also very oscillatory. So if you minimize this one, your function will not be oscillator. So therefore another way to minimize even the higher order derivative. So this is essentially the total variation of the derivative, and this is the total variation of the derivative. So that's another way to do it. I think you see like higher order. So if you minimize this one, so therefore you see mostly we read this one d square. You still use Lagrange, you minimize with the u, yeah. And so here is the second order derivatives. If you minimize this one, you will get what's the order of the partial differential equation? And then you will get the fourth order partial differential equation, and still nonlinear. So therefore, I think recently in the past 1 or 2 years, instead of just minimizing the first order, but you minimize the higher order derivatives, was getting popular for image processing. So there's a lot of new things related to those ones. So therefore, instead of minimizing first order derivatives, you minimize the second order derivatives. So therefore, you see that this will be, you will get some partial differential equations. Especially you see that to give an intuition about why minimize the higher order derivatives can overcome some of the weak point of the lower order derivative. So therefore you see that this is the routing Auger-Fatami. This is the minimization of the second order derivatives. And this is one of the, So therefore if you look at the corresponding linear equations, just 1D, you see that this will be the second order heat conductivity in 1 dimension, and this will be the fourth order heat conductivity in 1 dimension. You notice there's a minus here, there's a plus here. Yeah. So therefore this is second order heat conductivity, this is a fourth order heat conductivity. And then you see that, so earlier we have been using the kernel. We're using the heat kernel to explain the noise removal property. So now you see that if we use the Fourier analysis, if you look at the Fourier analysis of those two equations, what you will get. So even Fourier analysis, for example, we can choose the interval. Yeah, we can choose either infinity long or just choose a 0, 1. I think if you choose a 0, 1, choose a Neumann boundary condition, here should be cosine. But let's use a zero boundary condition, then it will be sine. This is not essential, just use the Fourier analysis. So therefore you see that if we look at those two linear partial differential equations, assuming your initial temperature can be expanded into all different frequencies. So these n indicate the frequency. And so this is the magnitude for that frequency. If your initial image can be expanded to this one. So therefore, if this contains noise, where the noise comes into this frequency expansion. If U0 contains a lot of noise, this noise comes to which frequency? Sorry? Yeah, so the noise mostly coming to the high frequency. The polluter low frequency, very little or nearly no low frequency. And so therefore, if you use this one to solve it, and this will be the solution. So here E minus n pi squared t. And so therefore for this one, here is wrong, here should be plus. All right. Because you do integration by 2 times, I will also use a plus. Here integration by only by. So therefore you see that for the fourth order partial differential equation, so this will be the solution. You get n pi 4 squared, and here will be the same. Yeah, so this will be the Fourier solution for those two equations, either with the infinite Lombard or just a 0, 1, but then the boundary condition will alter the sine or cosine. So therefore this will be the solution for the second order, so this will be a solution for the fourth order. If you look at those two solutions in the Fourier sense, why the first equation killed the high oscillation, that was you see that when t is a little bit bigger than 0, you see the high oscillation, this n is very big, right? So which means all the frequency due to this term, all the frequency will go to 0. But the high frequency go to 0 much faster. Right? Because if n is very big, n equal 1000 compared with n equal to 2, so this is 0 already for very, very small t, but the low frequency nearly you didn't change anything. So this is another way to explain, you see the frequency damping property for the partial differential equation. So this equation will kill the high frequency very, very quickly, but low frequency touch very little. So therefore if you choose a small t, and the high frequency already disappeared, the low frequency are still essentially the same. So this is yeah. But however, if you look at this equation, and what are the differences of those two equations?
High frequency disappears.
Yeah, so here you have a fourth power, here you have a second power. So this one will kill the high frequency even faster. Even faster. So therefore you can see that, if you use a second order, it kills the high frequency, but use a fourth order, the high frequency kills it even faster. So therefore you see that if here is a fourth order derivative, if you use sixth order derivative, and then here you will get a 6. So that means you see even higher order partial differential equations kill the oscillation even faster. So that means you can use a higher order. But there must be something, right? If you use a too higher order, there must be something you see that may come into play. Okay, but now also we have to see 2 points. So one point you see the linear equation, you can use a Gaussian kernel to explain how do you kill the oscillation. The Fourier analysis is another way to look at the equation, how do you kill oscillations. So therefore here is you can do test. Here is the input signal, here is the output signal, so you have a lot of noise. Here you see clearly where are the jumps. And so therefore you see that if you use first order, and this is what you get, total variation. So therefore you preserve the jump of the location exactly. There's no missing of those things. But then you can see, especially for here, you see the staircasing. Instead of a smooth function, you get a lot of small stairs, and this is in 2D, this is the oil painting. But if you're the false order Pde, so you don't get the staircasing. So at least you don't, essentially there's no staircasing, no staircasing. But here is you use a 6th order Pde. Also you don't get staircasing, but the function looks more, you see that you get more variation here. Also you get the Gibbs phenomena. You get the Gibbs phenomena at discontinuities. And this is even this is the nonlinear version, not the linear version. This is a nonlinear version. So therefore, you see that the higher order is higher order. You see that the lower order you get staircasing, higher order better. You get even higher order. You see you get the Gibbs phenomena. You get more variation. So therefore, it's not sure. You see that the order of the Pde should go very, very, very much higher, very, very much higher. Yeah. And so therefore those are the elementary ideas to use a partial differential equation for image processing. So therefore you see that the first crucial idea is that you found a mathematical tool such that you preserve discontinuities. So image processing, the discontinuity is the most important thing. If you can't handle the discontinuity properly, it will not be good for image processing. That's a different for surface processing. If you want to process a surface, construct surface, normally there is no discontinuity. But for image processing, discontinuity is a crucial thing. So I think this is the most elementary idea. So after this one, I will just talk a little bit about Montfaucon and the elasticos and some variation of this one, and then we go to the fast numerical schemes. Most probably you see today, tomorrow we'll finish these things, and then we move to the more exciting things after this one. So maybe let's take a break now. Yeah.
5 minutes?
15?
15?
Yes. Have a better relaxation.
Break before you break the numbers.
Okay. It goes too quick. So, but however, I think this part maybe it's quite easy for most of you. So maybe it's okay. We go a little bit faster. For the later part, so we can, you see, especially if you ask questions, if we discuss, and then that will make things much easier, much easier. Yeah, because this part may be a little bit too easy. So let's continue, right? So therefore, instead of so we have introduced the discontinuity preserving is regularization. Normally, you see that essentially you call that term a regularization term. The last one is a fitting term. So the fitting term, yeah. So essentially, you see that like here, yeah. So mostly you see that this is yeah, mostly you call this a regularization term. This is a fitting term. So you regularize this term. The minimization of this term will make the image regular. Oscillatory is not regular. Yeah, even discontinuity is not regular. But you see here we want the discontinuity, so we just kill. So this is regularization, and this is a fitting term. So therefore, you see TV is a discontinuity preserving regularization. You can also use a higher order. You can also use a higher order, right? So therefore, you see that yeah. So here is a lot of comparison between the TV and the false order. So therefore, you see that here is especially the original image. We just plot the contours, and here you add the noisy only to the second half. You plot the contour. So therefore, if you add a little noise, and then the level curve are somehow completely destroyed, the level curve is getting too oscillatory. And so therefore, if you use the second order, so there's some more image later, you see the level curves. If you use a false order, the level curves looks more natural. Looks more natural. So this is false order. Later, I have one image. Maybe let's go to that image even now. You see that here is another comparison. Here is the level curve of the Lena image by the total variation. You see that if you add a little noise in the level curve will destroy it. If you use a TV, you see you recover the level curve somehow. But the level curve, you see that it's not so smooth. Here, if you use a false order, it's another false order. You can see the level curve are much more natural, much more smooth. Here is if you use a TV. So it's you kill all the oscillation, but if the higher order was even better. But in fact, this one was not by the false order there. This one by the elasticas. So we will try to come to elasticas later. Yeah. So we were talking about this image. So you add a half, and then you remove the noise, and this is a lot of numerical comparison between the false order and the second order. Let's skip those things. Maybe we also skip. So therefore, the false order is in fact is related to another thing. So the false order Pde. So false order Pde, you see that if you solve a false order Pde, you can decouple it to solve two second order Pdes. Right. If you do that one, so you see that, so this is a standard technique for partial differential equation. You solve a higher order Pde, you can introduce some auxiliary variables and reduce the order, but you solve two equations. You solve a false order Pde, you can introduce two auxiliary variables, and you can solve two second order Pde. If you do that one, there is a physical meaning. One of the physical meaning that one of the Pde is not processing the partial differential equation, but processing the derivative. One of the Pde will do that. If you do that one, so you see why not just directly first process the derivative. So therefore, if this is an image, if this is a surface plot, and here you can see the corresponding contour. And so therefore you see that if this is non-zero gradient u divided by this one, this is I write n. So what's the geometrical meaning of this n? This you should have learned in the calculus. What's the geometrical meaning of this n? Huh? Yeah, this is a unit normal derivative to the level curves. So this will be unit normal derivative to the level curve. So therefore, if you rotate it by 90 degrees, so here should be y, here should be y, here should be x. Yeah, so here there's a tempo, here should be y here. If you rotate it by 90 degrees, so this will be the tangent vectors. Those will be tangent vector to the level curve. So therefore, you see that to solve higher order Pde is somehow you first process those derivatives, and then you see recover the image from those derivatives. So why not do it directly? So therefore, you see that here is the true unit normals. If you just add a little noise, here will be the unit normal from the noise images. So here you can still see some kind of pattern. But once you add a little noise, you see nearly no pattern at all. No pattern at all. So therefore you see that you can still process, here's normal. But if you do a smoothing, suddenly you get so good. Just do smooth the noisy vector, unit normal vectors, and this is what you get. And so there was just you smoothing this one, you get this one. And you see a lot of structure, but it was over smooth compared with the true normals. It was over smooth compared with the true normal. So here is the true normals. Here is a smooth one. You see that it's not the same, but looks quite, you see that somewhere it was over smoothed. You see, especially here. You see here, you see that it was over smooth. This part was well recovered. This part was well recovered. If you see more clearly, you see that corner is over smooth, but still you see that the smooth normals contain a lot of information. So therefore, one way is instead of directly you see process the image, you first process the normals, and then you see that once you get the normal, here is the normals, and you can try to recover image such that the image unit normals fit into this vector. That's another way to do false order processing. Do you capture what I'm saying? Instead of solving false order partial differential equation, so you first smooth the normals. So here is the noisy normals. You smooth it, you get this one. And then you try to find the image such that this image, the normal fitting to this one. So that's another way to use a higher order partial differential equation. So mathematically, essentially you see that you solve two ways. So you first give an image U0, you calculate the noise unit normals, you smooth those noisy images, so that here is the total variation of a vector. So we briefly talked about it, but we didn't go further. So instead of a smooth image, you smooth a vector. So similarly, so here is the total variation of the vector. Here you put this one, but this vector, you see that need to be a unit normal vector. You put this one as a constant. So this is the first part. That's what I showed in that image. You smooth the normal vectors, and after you smooth normal vectors, how do you recover image? So therefore you see that, and then I want to recover image, and so here, so this one will be the unit normal vector. If you recover image D, and those are unit vector, and then you will ask this one to be as close. N0 is a noisy one, and here is a smooth one. So you want to ask your new image and equal to this one as much as possible, right? This you can do by least square, but that will smear out things. So therefore, instead of doing least square, so you can do this kind of, even there are different ways. So you can do this one. So essentially you see that here is a recovered N, and here is the unit normal of the image I'm going to recover. Assume they have the angle is alpha. Angle is alpha. And so therefore you can see that this term equal to what? That term is essentially equal to gradient D. Here is minus gradient D inner product with N. So this is essentially equal to gradient D minus gradient D normal N cosine alpha, right? But however, this one we impose a unit vector, so that this is equal to 1. So therefore you take it out. So here is a gradient D. So here is 1 minus cosine alpha dx dy, right? So assuming you see that if you minimize this term, what's the meaning?
Minimize angle or minimize gradient?
Yeah, this is no. This one, this is not okay. So this is also minimized, and so essentially you have an effect to minimize this term. This term equal to 0 if alpha equal to 0 or 2 pi, you see that. So therefore essentially trying to minimize, to get this term equal to 0 is essentially trying to get alpha equal to 0. So which means that you try to, you see this angle is matched as much as possible. So that's a second step. So once you recover N, you try to find the image such that this one is as close to N as possible. How do you do it? So that was essentially minimize this. So the first term is trying to get the angle of those two as close as possible. And here, because you see we have a noise image, we can also, you see, balance those two parts. So therefore you see that, so if you do those two, so that was somehow equivalent to minimize. So first process the normal vector, and then and so this part we use, essentially the method we use was in a paper due to Vesey and Osher, I think it was published in some journal in America. We use that method to compute that part. The second part is essentially the TV. Especially the second part, I can't remember. I didn't write down So therefore, the second part, if you do the Euler-Lagrange equation, in fact, this is what you get. So you do the Euler-Lagrange equation, you get this one. Divergence D minus N plus lambda, so D minus D0 equal to 0. So therefore you see the difference with the ROF model is that here we have, if you take n equal to 0, this is essentially ROF model. Right. So what is more ROF? You see that is, so the ROF model was essentially trying to match this one to a 0 vector. But here you see we put the n here. So you can see that this will be definitely better than the ROF. But however, you should preserve the discontinuity. I shouldn't say you see this is the best methods, but you see that if you really want to get the image which is much better, and this is the direction where you can go. You see the ROF could be the starting point. You see that here you see you just put you have an estimation of the directions. If you do this one, so it will make it better. Yeah. So this is essentially, you see that instead of directly processing the function, you could always process the derivatives, and once you get the derivatives, and then you recover the function, right? So you can even go higher. You see that instead of the derivative, you recover the curvature. From curvature you recover the derivative, and then from the derivative recover the function. I think these for some application will be definitely better, right? So let's skip those ones. Yeah. So therefore, after the total variation and the higher order derivatives, so I think the Mumford-Shah model is one of the mostly talked and used. And for image processing, and this one, so therefore you see I will talk more in the second part. We mostly use it for image segmentation. We'll talk more in the second part. So therefore you see we will not talk about here. So later we'll talk much more about the Mumford-Shah and how to use it for segmentation, right? There's another thing is the so-called elasticas. So this one I think is very difficult to compute, but nowadays you see you can compute very quickly, very quick. So the elasticas is essentially for a 2D curve. For the 2D curve, assuming k is a curvature. So curvature measures how quickly a curve is turning, right? If you have a straight line, the curvature is 0. You have a circle, you have a constant curvature. So therefore, if an arbitrary curve, if the curvature is big there, that means you have a turning very sharply. If the curvature is low, you see the curve essentially goes in a constant direction. It doesn't turn. So therefore, you see that essentially this is measuring the bending energy of a curve. So therefore, if b equal to 0, so this is essentially the length times the constant a. If a equal to 0, and this is just a measure is a bending energy. So therefore the elasticas energy for a given curve is that you combine those two. So therefore you see that elasticas has a lot of applications for mechanics. If you go to mechanical engineering, so there's a lot of simulation for elasticas. But for image processing is essentially you see that assume I give a function u which is a represent image. And then you see that if you cut the function, you get a lot of level curves. You see here for every given tau is one level curve. You give another tau, you get another level curve. So therefore when tau varies, you get a lot of different level curves. And so therefore you see that this will be the elasticas for one level curve, right? So this measures, this will be elastic of one level curve. And then you see here for a given tau, if you integrate with the tau, so this will be the total elasticas. It's not one level curve, you see elastic for all level curves. So therefore you see that what kind of curve the elasticas will be high. For what kind of curve you get very high elasticas? oscillatory curve, you get very high elastic. But even you see that if you take B equal to 0, so therefore you see that these kind of oscillatory curves, you see you have this well-known curve. You see that you just add a triangle here, add a triangle here, add a triangle here. You see that for this one, you see that the length is still bounded, but the elasticas will go to very, very high. So sometimes only regular length is not enough. You see oscillatory curve can have a small length, but you see once adding this bending energy, you will get the curve even much more regular. So you not only minimize the length, but also you minimize, you see how the curve is turning and bending. And so this is one curve integrated with all the tau, so that will give the total elasticas of an image. So therefore we use it for image processing. And so therefore you see that for the level curve of a given function, the curvature is essentially equal to this one. If the function is smooth and there is nowhere the gradient equal to 0. And this is the curvature of the level curves. And do you know how to calculate this one? Why this is correct? So it's some fundamental calculations. So you can parameterize the curve by x, s, y, s. You calculate the curvature, and they use the implicit function, right? You can. So the curvature of the level curves is equal to this one. And then you see either you can use this formula or use a co-area formula. So therefore the co-area formula for 2D functions was essentially, the co-area formula essentially a function is that, so you get, so I have a co-area formula somewhere there. So this is the so-called co-area formula. So therefore, omega, if you just use Wikipedia over the internet, you get the co-area formula. So here is the dx, and this is for arbitrary gx, and this is equal to minus infinity, positive infinity. So here is all the level curves, u equal to tau. So here is a g, x, so this is a, right, so this is a so-called co-area formula. If you integration this one, and that was the integration of this one with the arc length. So here is with the arc length. So you integrate over the arc length for all the time levels, and then integrate the level, and this is equal to this one. If you do this one, so therefore you see that, and this one, in fact, I got it from Wikipedia. You just Google search Wikipedia co-area formula, you will get this one. You'll get this one. So therefore, if you use a co-area formula, and then just use this one, so essentially you put this one as a G. You put this one as a G, and use this formula, and so therefore this is essentially, this becomes the total elasticas of all the level curves. So you integrate the elasticas of all the different level curves. So therefore you see that if b equal to 0, this reduces to the TV, the total variation. And also this is it shows that the minimize the TV is minimize the sum of the length of all the level curves, right? Because the total variation is essentially, you see that, right? So this is if you take a b equal to 0, so this is you see that you just calculate the length of all the level curves and then integrate with all the levels. So therefore, minimize the TV is essentially minimize the total length of all the level curves. Instead of just minimize the total length, you can minimize the total elasticas of all the level curves, And this will be total elasticas. So instead of using TV as a regularization term, so therefore you see that you can use a total elasticas instead of minimizing the TV. You minimize the total elasticas. So therefore give an image. So here is a U. So U is given on gamma. So therefore if you do this one, so therefore this will be another way to regularize the image. Right, regularize image. Essentially you see that here are two questions. So what kind of a PDE we will get? Can we get any hint of what kind of PDE we will get? You see, you minimize this one. It's not solving this one. So you do minimize. So which means that you need a variation. You need to do variation on this term. You need to variation. You see, even this is a product. So can you give any hint? I think, yeah. Can you give any hint of what kind of PDE we should get? Right. So, sorry? Nonlinear, yeah, false order. So therefore, if a B equal to 0, so your variation of this one, you see that mostly your variation, the derivative, you get second order PDE due to the integration by part. But here you see you have a divergence. Here is a gradient dot. There's a divergence. You have a gradient. So therefore, if you put this one, you will get a second order derivative mix with the first order derivative. If you do variation, so the false order should come from this one. It's a very, very complicated false order. I think the elasticas, to introduce elastic for image processing, I think it can trace back by the very old paper by Mumford with two collaborators. I think later, and the French people, what was the name, Musso, they use elasticas for inpainting. So I think they was really made popular by Tony Chang, Sung Hwa Kang is a Korean, Sung Hwa Kang and Jackie Shin. I think their paper was really the crucial paper to make the elasticas popular for image processing. But they have used it for image inpainting. But in fact, you can use it for denoising, inpainting, zooming. There's no way just to use it for inpainting. So that's the reason you see we put the gamma here. So we put the gamma here for different applications. You just use a different gamma. I think maybe even I have a slide in the next part. So for example, for denoising, which means that U0 is given for on gamma. For denoising, you see that the noisy image is given everywhere. So therefore, you see just take omega equal to gamma. So then if you choose the A and B properly, so this will remove the noise. And then the noise image, not only the level curve have, you minimize the length, but you also minimize with the curvature. So therefore this will be for denoising. And for inpainting, so for inpainting mostly is that you have an image. So therefore you see this part, the missing. And here is a gamma. In the gamma part, so therefore this is the image is known. The image is known. So therefore the elasticas, you see that you have a level curve outside. So those are the curves, the level contours outside the image. You want to connect the level curve. You see the same level, you want to connect them. When you connect the curve, so you not only want the length to be minimized, you also want the curvature to be minimized. That's the reason you minimize these elasticas. So essentially you minimize, so the total elasticas A plus B divergence square and this one, and then mostly choose a small epsilon, and then gamma U minus U0. So therefore you see that this is the total elasticas. Mostly you see that was elastic in this region. Is this clear? So especially you see that when epsilon goes to 0, that was essentially you don't solve anything in the gamma region. You just use these boundary conditions here. You solve the elasticas in this region, which minimize the elasticas. And so therefore you can also use it for zooming. I think most probably. So therefore for image zooming, so essentially you see you have an image. And so therefore it's very coarse. And so therefore you have a pixel value here. Assuming you want to zoom it 3 times bigger, and then you see that you need to insert 2 here, right? So therefore there's you see all those points. You can do linear interpolation, bicubic interpolation, anything, right? But all those methods would have some kind of disadvantage. So to minimize the elasticas, so essentially the gamma equal to the cos pixels. So you see that, and then the gamma equal to the cos pixel, u is only in the cos pixel. And you try to recover a new image which has, you see the total elasticas should be minimized, but on those cos grid, you should equal to the original value as much as possible. So this you could use this one as a zooming. You could use this one as a zooming, right? So therefore you see conceptually this is 1 step higher than the TV, right? So you not only control the level curves, but you also control the curvature of the level curves. So therefore TV, you see mostly you see the length is minimized, but the curve doesn't look so natural. But mostly if you use the elasticas, the curves looks more natural. So conceptually this is one order higher. But the problem is see that this equation is how to solve it. The problem you see that this equation is very complicated. Even you see that I think in the paper by Chang Kang Shen, there is a derivation about Euler-Lagrange equation. I can't do it by myself. To find the Euler-Lagrange equation for this term, I can't manage. It was very complicated, very complicated. There's another thing that computationally is very costly, because the false order Pde, so therefore you must use a very small time step. Very small time step. So therefore for ROF mostly if you use explicit time matching, it takes about a few thousand steps. But for this one, if you use explicit time matching, mostly it takes some million steps. So it's only not a few thousand, it's really millions of time steps. But that's a past. There are new methods which can really solve this one very quickly. We have a paper using Lagrange, which you can solve it very quickly. Number of seconds you can solve it. So therefore you see solving of this equation is not a problem. Anymore. So yeah, so the original plan was for the Mumford-Shah I will talk quite a lot in the second part. For the first numerical scheme, so I was thinking to talk about 2 methods. One is called the AOS, so which is the additive operator splitting scheme, and then I will then talk about Lagrange. So there were a number of other methods. So therefore, we don't have time to talk about all of them. So I will pick out the AOS and the Lagrange. Mostly we will do that maybe by tomorrow. So and then we finish those things and then we go to the second part. The AOS is called additive operator splitting scheme, and the Lagrange is something. This is really due to the split Bregman. So split Bregman by Stanley Osher and Tom Gustin. So that turns out to be one of the quickest methods for ROF. But later you see that people found out the split Bregman is just Lagrange. But the if you can, the split Bregman, you can use it for RF, but if you really use it formulated Lagrangian, and you can use it for a large number of problems, include the Euler's elasticus. Also numerically it turns out very, very fast. Most of the, if you use Lagrangian, mostly turns out very, very fast. I think that was, I intend to talk this one. Maybe you see also I quickly show you what I plan to talk about the second part. So this is what I plan to talk about the second part. That one maybe most probably we start from next Monday. So I will talk about graph cards and P minimization for image processing. So essentially I will concentrate on you see on segmentation, introduce the older methods. You see what are the elementary models, and then I will talk about you see level set methods, and this is still for many of you the Transversal model. The Transversal model. You see the piecewise constant things. And then the phase field things. And especially the convex relaxation, that was the convex relaxation things, which turns out very fast, very stable, combined with Lagrangian. Then I talk about graph card, yeah. So this one I'll point out a number of relationships, and then the multi-phase transversal. You see also the even more phases. So using continuous card or different things. I think this part is quite exciting. So therefore, that was the next part of the lecture. Yeah, next part of the lecture. All right. So that was. So maybe today we just finish here. So tomorrow we go through in somehow quite detail, go through those fast algorithms. Okay. Thank you for coming to the lecture. Yeah.